So now we're going to do the spherical coordinates for the heat diffusion equation. And just like the last video, or I guess like the first half of this video, I wrote out a diagram again. And you can see here that instead of Qx, Qz, and Qy all going in, it's going to be Q phi, Q theta, and Qr. And then the heat flows exiting the system are going to be Q theta plus d theta, Q phi plus d phi, and Qr plus dr. And so to start off with this, we're going to write out the heat fluxes because this is going to be a little different than the Cartesian coordinates. So the first heat flux we're going to do is QR, and it's going to equal QR. It's going to equal negative K dt over dr. And then, so this is going to be in watts per meter squared because it's a heat flux, and then this is going to be in, K is going to be in watts per meters per Kelvin, watts over meters per Kelvin, and then this is going to, the temperature is going to be in Kelvin per meter. So this is for QR, and this all works out with the units, but if we were to write Q phi using the same reasoning as this, it'll be a little different. So Q phi equals negative K partial T over d phi. So you would think it would just be d phi because that's what we've been doing previously and it works out for R like that. But if it was just d phi, then that would be radians on the bottom, and radians are almost like basically unitless. So you need some sort of distance down there, and the distance that we're going to use is r sine theta for this. So it should be r sine theta d phi for that. And then that way all the units work out for this. And then so now that we've identified the heat fluxes properly, now we're gonna write the heat flows out. So heat flows, so QR is gonna be r squared sine theta d theta d phi, because this is going to be your area, times negative K dt over dr. So this is your QR. So you're multiplying by the area in order to have the proper units of watts. And then Q theta is going to be r sine theta d phi r times negative K dt d theta. It's not subtracting, it's multiplying, by the way. I think that looks right. Yep. And then, so Q phi is going to be r d theta dr times negative K dt over not d phi, sorry. You're going to use the heat flux term here, so it's r sine theta d phi. So these are all of your heat flows for each part, and then just like we did in the last video, we're going to also be able to do a Taylor series expansion for all the heat flows leaving the system, which I'll probably need to erase this. So, I will just erase all of that, I guess. So, QR plus DR equals QR. So QR over DR. So this is the same format that it was for the last video, so I'll just write it out. Okay, so for this, it's going to be, this is just the heat flow in the radial direction, and then this is the sensitivity of the heat flow. It's going to be the same for these two, so it'll be the heat flow in theta direction or the phi direction and the sensitivity of the heat flow for that. And then, so the next part, you are going to have to write an energy balance just like we did in the last video. It'll be the same concept. It'll just be energy stored equals energy generated plus E in minus E out. So this you can simplify for each R, theta, and phi, which I'm probably going to cut the video just because I'm going to need the whole whiteboard to write it out for each of them, but yeah. Okay, so now we're going to simplify with doing QR minus QR plus DR, just so simplify everything down, which is just going to be the negative partial derivative of QR over partial derivative R, DR, and from here you can simplify the stuff from the last part, so it would be sine theta d theta d phi dr, so it'll be area, and I think you're also going to have to multiply by, this will be squared, so it'll be r squared k t r. So that'll be just after they subtract and plug everything back in. Yes. So then you can do q theta minus q theta plus d theta, which equals negative partial derivative q theta d theta times d theta. And then you can just plug in for q theta, and you get d theta times d phi dr times partial derivative theta. What time is that from? Oh, this doesn't need it. Whatever. But theta equals sine theta times k over d theta. Okay. And then now you can do q phi. Q phi plus d phi equals, it'll be negative partial derivative q phi over r sine theta d phi times phi. So So once you have all of these out, then I would write the energy balance, or we have to write the equations for the energy stored and the energy generated in order to plug everything else back in to simplify. So first we can do the energy stored first, which is going to be similar to the first video where you have rho and Cp and the temperature, so it would be the partial derivative of rho Cp. And you need density because you're talking about position and not mass. That's what you have to multiply by density, and then the temperature, and then you're also going to have the volume, which will be r squared sine theta d theta dr and d phi. And then it'll be over the partial derivative of time. And then energy generated. This is also going to be similar from the Cartesian coordinates. It's just going to be q times r squared sine theta d theta dr d phi, which this is going to be your volume. And then this is going to be the energy generated rate per unit volume. And then from here, you can plug everything in to, let me write, so energy stored equals energy generated plus in minus out. So that's your energy balance there. So from here, you can plug all of these back in because this here is your energy in minus energy out for r, theta, and phi. And then you have your energy generated here, energy stored. You plug all of that back in. And let's see if I can fit this all in here. So you're going to have so this is going to be able to cancel out because you'll divide by the volume for everything. Energy generated is Q. And then plus 1 over r squared. R squared. And, oh, I don't think you can now. I think you can now. Can you see it? R squared. Right. And then split the R, and then do theta, which will be I don't know if you can still see that. I think that's plus 1 over r squared sine squared theta d phi. Okay, so there you go. This is spherical coordinates for the heat diffusion equation. Yeah, thank you.